Hi there, welcome back. Welcome to the second video in the restoration series for this Braun T1000CD. And before we get started, I just wanted to show you what the bench looks like when I get this thing in full swing. It sort of scares me sometimes. But everything is needed, and every now and then I got to do is stop and just put most of the stuff away so I get some space. I've got the schematics there, that's the board. I managed to get, besides the service manual that the owner had with him, the file, I managed to get some very good resolution schematics for this. So I'm working with the schematic and the board layout at the same time. Obviously, on the actual amp board that we're looking at first. And here it is here. And it was not as bad as I thought it would be. It was worse. And I'll tell you why it was worse. I know this sounds all too bloody dramatic. This is not supposed to be soap opera. It's supposed to be restoration videos. But as you can see, the two transistors there, these guys, they're not original. These are ones that I've put in temporarily for the simple reason that there were no transistors there. The two output transistors were simply gone, as were quite a few of the other components. And what I've done is I've gone and started looking at this board, literally component by component, connection by connection. And then, of course, relating everything to the board layout here. And of course the schematic as well, and painting it off like I usually do. Now I'm going to go into a bit more detail as to what's been done. You can see there's quite a bit painted there, and what is painted tells quite a story. So stick around if you want to see the result on this board. I'm hoping that we'll be able to actually test this. Now that would be great. And when I mean test it, I mean test it as a power amplifier and a voltage well, it's a power supply section of the radio providing various voltages to the different circuits. So yeah, what I want to see out of this is I want to see a signal from the signal generator coming in here and appearing on there. And I want to see a nice sine wave. And it's going to be a challenge because I don't have the original transistors. I've had to get creative. But I've been able to find the originals on a site in the UK, so they're on order. So the ones I'm putting in now are basically just to get this thing functional. Let's get into some more detail. This section, outlined in magenta, is the schematic within the board that we have on the bench. So that's what interests us most right now. However, there's something we need to look at first, which is the supply, and this will tell us how to bring power into the board. That section is down here, and it does the connection of the batteries, and it also handles the switching that we need to get power into the board. So let's look at that a bit more closely. So first of all, we have the two battery sets, 8 of 1.5 volts providing 12 volts, which is the main supply over here, and that 1.5 volt cell is for illumination, which we'll forget for now. But let's look at this part first. If we take the negative, if we look at the negative, we have the negative coming in here and it goes into the board. Once it's in the board over here, you see that it basically creates a negative rail down here. There's a small filter cap here, which is just to clean up the supply a bit more. And then it goes off to various places. The first one is down here, and it goes to what they call a power supply jack. Now, I haven't found this supply jack. I don't know if it's been removed, but this would be where your external line voltage module would provide your negative voltage here, negative supply. So we're not worried about that. Where else does it go? It goes to this section here, which makes that a negative supply. It makes that negative supply as well. And it also connects to the center tap on the secondaries of the output transformer, which is over here. Now, the output transformer then has one tap that goes off to one side of the speaker, and the other one goes off to the other side of the speakers. We'll look at that in a second. Let's look at the positive power. The positive supply comes out of the battery and goes into the set. It then, inside in the board, it meets a similar small filter cap like we had on the negative rail, and it immediately leaves the board. Once it leaves the board, let's follow it. It goes down here, and goes to the switch. Now, what does the switch do? Well, this switch is the selector between line voltage or battery voltage. And if it's on battery, what we find is that this connection is made, so we're following the supply. It then gets to here, and it meets the on-off switch, the main power on-off switch. And in the on position, that connection is made, so it'll go up here, up there, and it comes back into the board. And where it comes back into the board, it then creates a supply rail, a positive 12 volts supply rail over there. It also goes up to there, and that's also plus 12 volts. So we've got the main supplies, we know where they're going, and we'll take it one step further. Let's just focus on this for now because it is pertinent later. What we have here is a Zener diode, and I believe it's 2.8 volt Zener diode, and that basically is connected between the positive 12 volts and 0 volts. Now bear in mind 0 volt is not ground, because we saw at the bottom there that 0 volts and plus 12 volts were connected to earth or chassis ground via those 2.1 microfarad capacitors. So we're going to talk about 0 volts as opposed to ground at this stage. This thing creates a voltage over here, which is that amount less than 12. So if this is 2.8 volts, then what we're getting is minus 2.8 volts from 12 is 9.2 volts over here. And we'll see what that's for in a second. So that is over there. That actually comes down to that point there, and we'll just remember that that is about 9.2 volts at this point. Now let's look at the push-pull section. How does this thing work? Well, 12 volts goes through that 1 ohm resistor to there, and it meets these two emitters of these two PNP transistors. And what you've got here is effectively a normal push-pull arrangement where these two transistors, they're being fed with a signal that's in reverse phase to each other. So when this one goes up, that one goes down, and what happens is across this transformer your audio signal is being presented. So what you get is this generates the audio. Those two transistors are creating the audio. What we have in the middle here, we'll just paint that in as well, is a filter network which basically removes high frequencies and prevents oscillation and so on. It's just a resistor capacitor network which creates a cut at a certain frequency. I'm not sure what frequency that is, and it's not important right now. So how's this biased? Well, what they do is they take the 12 volts over here. It goes through that 100 ohm resistor. It should go through that trimmer as well, but that trimmer doesn't exist on the board, and we may not need it because it's only in parallel with this 100 ohm resistor. So we'll see if we need it or not. And then it also has a small filter cap over here, which we don't need to focus too much attention on. But what we've got here is a supply rail which goes to the center tap of that interstage transformer. You got basically almost 12 volts here. And that goes up there and it comes to the base of that transistor. And it also comes to the base of that transistor. Now what we've got here, if we ignore this section here, we would have 12 volts there, going through there, practically 12 volts there too, a little bit lower because you've got a bit of current being drawn, and it drops the voltage slightly because of that 100 ohms. So let's say it drops 1 volt, okay? If it drops 1 volt, what you've got here is this thing goes in there, it goes through there. Say you've got 11 here. You will have practically 11 there too, because this is a very small resistance. It's just an inductor, and we're talking about DC voltages and DC currents. So you would have 11 over here. If you have 11 over here, and this thing is at 12, as we've seen through this line, this thing would be switched hard on. So you don't want 11 over there, you want something controllable. And the way to control that is by using that voltage, that lower voltage that comes from the top there, which gives us about 9 point something here. And these two together allow you to trim by adjusting there. You can trim this so that you create this voltage just slightly lower than 12 volts. When I say just slightly, what you want is to get these two transistors to just start conducting. In other words, you're setting up a quiescent point, a bias point, and if these things are just starting to conduct, and the amount they tell us that they want is 10 milliamps, so these two transistors should pass 10 milliamps through the transformer, and you adjust it by adjusting the voltage that's on the base, which is adjusted through that trimmer pot there. Now, the transistors I have in here at the moment, the ones I've replaced the originals with, the non-existent originals with, they're PNPs, and they would require a bigger voltage, a bigger bias difference here. So we need to determine whether that range that this trimmer gives us is sufficient to get these two to start conducting. And as we'll see, I'll show you how it's done. They do start conducting. There's actually a point in the PCB which you remove a short, you put a milliammeter across there, and you can adjust it till you see 10 milliamps flowing through this circuit here. And you know these things have just been biased correctly. Now, what happens here? Once you look at this section, it makes a lot more sense. This is connected to 0 volts, through there, and it goes to a driver transistor where your audio is being driven through that primary, and it's coming out as 2 equal and opposite secondary signals. I'm not sure what the gain or not of this section is. It could be 1-to-1 as well, but it creates the push-pull, the phase inversion, as it were, to drive these transistors. So the first experiment I want to show you here is I want to show you how we bias these two, and then I want to show you what happens when you feed an audio signal into there as if the transistor was working. What they want you to do is to break this link where it says 10 milliamps over here. You break this link and you connect a milliammeter across these 2 points. Then you power it up with 12 volts and you adjust this trimmer till you get 10 milliamps flowing through there, which tells you that the 2 output drivers are properly biased. Now, the amount of adjustment you need to do depends on the characteristics of the output transistors, and because ours are silicon with a higher bias voltage, we'll need to see whether the range that this thing gives us is sufficient to actually bias them. Then, when you've got that set, you short this out again, okay? And then what you do is we need to simulate this transistor here providing a signal. So we're actually going to input an audio signal at this point, which goes down here, down here, down here to that transformer. And we should be able to see at the output, which is actually, if you follow this transformer here, there's the one winding, goes to there, the other one goes to there. So these 2 tracks over here, which is that one and that one, are your speaker out, 15 and 16. So let's set that up and see what we get. We're all set. We've got this meter measuring the current across that link. I'd soldered 2 little wires on here just to make it easy for us. This one's hanging around just to use if necessary, reference to ground. The power supply is set to 12 volts and I've got 40 milliamp current limit. I'm not that brave. So we'll switch it on, see what happens. Absolutely nothing. But that's not a surprise. Let's see what voltages we've got on the transistor. There's 12 volts coming in. on our two emitters, we've got our 12 volts. And on the base, we've got 11.8. So we've got 0.2 volts difference across the base emitter junction of those two transistors, which is certainly not enough to turn them on. So we need to start messing with this trimmer. And I'm going to measure the voltage on the emitters as I do that, so that we get an idea if we're going the right way or not. I think it's there. No, looking at the base. Where's the base? There's the base. Okay, there's the base. 11.8. We want about 11.5, thereabouts. That's the right way. Oh, too much. Whoa, that was 20 milliamps. This thing is really sensitive. 1.4 milliamps on Big Brother, 1.9, 2, 3, 7, 9.7, 10.1. That's about right. That's too much. Bloody hell, this thing is really sensitive. 10.1 milliamps. Perfect. 11 point, call it 11.3, so that's a difference of 0.7 from our emitters. Maybe not, because now the voltage has dropped because it's going through that resistor. On the emitter we got 11.9. So 11.9 on the emitters, 11.3, so 0.6 volts is what we needed, and those two are biased. So now what I can do, switch that off, is I can actually remove this and I can solder. I'm going to just turn these two together, wrap them up, but let's leave it there for now. So we've now shorted that out. We can get this out of the way. And now what I'm going to do is I'm going to supply a signal, and the signal is going to be referenced to 0 volts. And I'm going to input the signal right there where that driver transistor's collector is. So this signal is feeding into this primary of that interstage transformer. And now we need to look at what we get on the scope. So now I've got everything switched on again, and I'm going to just connect the signal generator. I've got a 1 kilohertz sine wave and at 40 millivolts RMS. There we go. The one channel is connected to the one speaker output, referenced to 0 volts. The other channel is connected to the other speaker output, referenced to 0 volts. And what the speaker would see would be that, the maths function, the difference between the two. As you can see, it's double the amplitude of the first one. I'm going to increase the input signal, and it works perfectly. I'm at 100 millivolts, and what we have here is, looking at the yellow channel, 600 millivolts RMS, which means that the other one is also 600 millivolts RMS, which means the difference between the two is 1.2 volts RMS. So we're talking about, what is it? 1.44, very low amplitude, very low power in terms of speaker, what the speaker is seeing. But we've got that section working exactly as it should. So those transistors do quite well here. Just wondering whether I shouldn't leave them in. They're certainly more robust than the AC153Ks that I've ordered, but we'll see later. So, good stuff. Now, what we have here is we have that first transistor, the driver transistor, is being bypassed. I'm not actually using it at all because I'm feeding the signal to where its output is supposed to be. What happens if I go to the base of that? Oh dear. Starts going haywire. So that transistor is not good either. So that's the next stage we're going to look at. See what's happening with that transistor and see if there's something we can do about it. Now that transistor, just switch this off, is exactly the same. It's an AC153K. It's the same as the two drivers. So I think I can actually just replace it with exactly the same one that I used to replace the drivers. We'll have to see about the biasing though. Okay, but first stage works well. Let me carry on and get back to you. Okay, we've got some more progress. Let's have a look at this. This entire board has now been looked at. And I'm sure you'll agree, it looks a little bit different to what it did originally. That wasn't too difficult. All the solder was removed and renewed and cleaned and so on and so forth. So yeah, that's what we got. Now let's look at the top side. And this is what we have. Now, as I said before, these two transistors are silicon PNPs. They're there temporarily. What I found was, I started finding, in fact, the resistors, some of them were not too bad, but when cumulatively looked at, when you look at the effect of the transistors cumulatively, the tolerances were so out that they started affecting each other. So I decided to replace all resistors with metal film. The capacitors were all replaced except these two VMAs. They were perfectly fine, 400 microfarads at 15 volts, so I left them in. Those were all replaced, and what I decided to do, because these were axial and the new capacitors are obviously the ones I had were radial, I did that to them. So it makes it look a little bit more original, gives a bit more work, but at least it looks more decent. I like it. So I've replaced all the capacitors, and literally all the capacitors except those two. And then there are a couple of mysteries here. I said that this transistor, this pre-driver, or the driver of the interstage transformer, was not working. It actually is, and I will show you now when we do a test. These transistors are in fact working. I think they're both leaking a bit because their voltages, the voltages that you're supposed to measure, are not quite the same as what it says on the data sheet, on the schematic. But what this means is that they're fine for testing. Now I've got new ones on order. I've got these on order as well as these on order. And so I just went ahead and carried on completing it, testing it one step at a time. And I got to this stage here, which has the voltage regulation circuitry. There's one resistor there that was spot on, and in fact it's a difficult one to get. It's 4.3K. So I left that in there after removing it and testing it. And I think it's ready for testing. What I've found with the voltage section, this section over here is the one that provides the various voltages. It's supposed to provide, well, let me first explain. This thing has two grounds, as it were. The output stage, the two output transistors use the negative 12 volts or the 0 volts of the battery as their reference ground. And then everything else after that, there's a, actually the power amp section as well, the preamp section as well. But everything else works on chassis ground, which is separated from this negative 12 volts, which comes in here by a 100 ohm resistor. So whatever current is flowing on that section will create a voltage drop on that 100 ohm resistor, which will effectively make this point here more negative than the chassis ground. There's a voltage drop between the two because of the current flowing between the two. So you actually use two ground references. And when it comes to the voltage regulation circuitry up here, they actually suggest you use, or they tell you to use, the chassis ground as a reference. And the point for that would be this screw point over here. That is chassis ground. There's another link over here to it, but we can always use that to measure. And what I've found is, what I'm supposed to get on here is I'm supposed to get the B plus, the minus 12 volts, which no longer is minus 12 because you've got that current drop, or the voltage drop between the 0, the minus 12 as it were, and chassis ground. It's supposed to be 11 volts. Now, of course, we can't measure 11 volts, and the reason is very simple. We don't have any current being drawn from this, really. All the circuitry that this supplies will draw current. If it draws current, that current will then flow back through the chassis ground, see a 100 ohm resistor, and go through that 100 ohm resistor to the negative of the batteries, which is lower in voltage than it, which means that voltage drop between the minus 12 volts and the chassis ground will be anything from 0.5 to 1 point something volts, according to their information. So we can't really measure it accurately like this. We are getting the reference to chassis ground. It's supposed to be 11 volts. We're getting about 11.6 or something. The other one, which is the regulated voltage through this transistor, which is at the top there, that's created by a Zener diode, which is this thing over here. And that is supposed to give you 9.5 volts reference to chassis ground. Again, we cannot really determine that because we've got resistors that drop the voltage and there's no current being drawn. So effectively what we're getting is just an arbitrary voltage. It's not going to be real until we connect this to the circuit. There is another voltage, which is the one that goes to the oscillator section. That is supposed to be between 5.5 and 5.7, depending on whether you use AM or FM. Again, that's giving us 7 point something, which is perfectly acceptable because, again, there's no current draw. But let me go one step at a time. Let me show you what happens to the waveform, or rather, what the audio amp is doing. I have soldered in. I adjusted the current using that trim pot to 10 milliamps across there, and I've soldered a wire across there. I've shorted it. So now I'm going to set it up and we'll see what the waveform looks like. Okay, I know that looks like quite a mess, but what I have here connected is I have the signal generator connected. I'm using a capacitor from the signal generator because I don't really have that input reference to ground. The supplying circuit will provide a reference to ground, but at the moment I think there's some DC there, so I'll use it through a coupling cap. And then I've got the oscilloscope, one on each channel. I've got the dummy load actually connected up here, so we can see a load. And I'm going to show you the scope and see what we get. Okay, we are ready, I think. The power is on. And I'm going to activate the signal generator. There we go. Let me put it on speaker. We can actually hear it. Dummy load. There we go. There's our signal. I'll increase the signal itself. Now what I'm noticing, it's at 70 millivolts RMS input, and it's going through both of the, or all three audio stages. And what I'm noticing is there's a bit of distortion on there. Now obviously this could be just the, let me give it the joint signal. Put that on the same. There we go. So the purple is the A minus B, the difference signal. And what we can see is we've got ourselves our sine wave. Now, as I said, there seems to be, it's now at 100 millivolts RMS coming in. Let me just give it, I believe it's supposed to be 5 ohms, sorry, the speaker is 5 ohms. So I've got 4 ohm on the dummy load, and we start seeing some clipping, and we're not seeing symmetrical clipping, which tells us that the biasing of those transistors is not optimum. But the important thing is we've got this thing working. Let me drop this a little bit more. Our audio amplifier is working. And what I'm going to do next is I've ordered the transistors, and when those arrive, I'm going to replace these temporary ones I've got here and the old ones. I know the old ones are leaking badly because I've tested them, and some of the forward voltage on those on these transistors, it's so low that it indicates a leak. But this is not the point. The point is I wanted to make sure that this thing was working. And when I get those components, I will replace them, And I'll be able to then connect this, albeit outside its position. I'm going to connect this sort of on the side of the radio, not actually in its place, because I might need to adjust some of the biasing down here. So I'll probably be laying the board here and then wiring it all up to that section, ignoring the existing wires for now, because I want to make sure that when I feed when I use the switching that's on the front here and feed the signals to the outputs and connections that are in the front here, that this thing works before I then put it back in its place and I'm able to test the rest of it. I think there's a fair amount of work to do on here, and I'm not going to create another problem by putting it in place and then having to worry about breaking wires as I move it around. That's the one danger with these things. These interconnect wires are single core and they can break very easily. I mean, these things are quite old. 40, 50 years old, 50 something years old. Yeah, it deserves a bit of respect. But a lot of things need checking here. But obviously, as I said before, without knowing that this thing was working properly, there was no point going on. So that is the way I am tackling this. I think that's where I'll leave it for the moment and wait for components to arrive. And as soon as they do, I will make those changes there, get back to you on any difference that we might have noticed on this board, and then of course also perhaps report back on the interconnection to that board. There are certain things on this board over here that would just make that the experiment we've done so far work better, like the on-off switch, the battery/line switch, and so on, and the battery test switch. So we'll be able to test that as well. So we're taking this one step at a time, very slowly, and hopefully we'll end up with a beautiful result. Guys, thank you for watching. Thanks for all the comments that were left on the first video. I can see that this particular project fascinated a few, horrified many, like it did me. But it is a favorite of many people. And I really do appreciate your comments. There is quite a bit of this particular radio that I don't know. So if you have any information to impart, please feel free to comment below. And if you like the video, please subscribe, share, like, and all that jazz. And if you do want to support the channel directly, you can do so on Patreon, which has the link at the end. Thanks for watching. Bye for now.